Today we'll simulate a dummy process on TwinCAT using FB transfer function 1 from TC2 controller toolbox library. We will excite the system using a frequency sweep signal and record its response using TwinCAT scope. Finally, import the data into Matlab to perform system identification and compare the identified model with the true model defined in TwinCAT. A process can be seen as a black box, and it produces a response when excited by an input. For example, your process is a servo motor, the input is voltage, and the output is the shaft angle. A certain amount of volts will result in some angular displacement of the shaft. The set of mathematical operations that maps the relationship between the input and the output of a system is what we call a model. A model can be a transfer function, a state space representation, an ARMA model, etc. FB process is our dummy model function block, and it has one input and one output. Our auxiliary variables are an instance of the transfer function function block, float arrays for the numerator and denominator parameters. Note that you need to add TC2 utilities to your references so you can use the data type float as well as TC2 controller toolbox, and some parameters. In the first cycle that the function block gets called, the transfer function gets initialized. Our model is a second order transfer function, and the parameters are B0 is 0, B1 is 1, B2 is 2, A0 is 0.5, A1 is -1, and A2 is 1. This function block needs to know what's your PLC cycle time. The function block cycle time cannot be smaller than your PLC cycle time. A sine sweep input is a sine wave that has its frequency increased every period. By exciting the system like this, you can obtain responses throughout a wide range of input signals. If you're planning to do system identification, you may want to use this function block. For that reason, I've made it a little bit more reusable than FB process. The inputs are the initial sine period, the control time, the PLC time, the amplitude, and the offset of your sine wave. When doing this in the real world, you gotta be careful with your parameters and make sure that you do not exceed the hardware limits of your system. Remember, this is open loop response. Things can go really wrong here. If sine sweep isn't right for your setup, you can also do step response. Just make sure you excite your system throughout a wide range of input values. More data, better model. In this function block, I'm using backoff signal generator to create a sine wave, but it can also be used to create a sawtooth or a triangular signal, depending on the value of the enumeration e-signal type. 0 for triangle, 1 for sine, and 2 for sawtooth. Like the previous function block, we initialize the parameters in the first cycle, but we keep the sine wave period out of this initialization. Then, if the period is greater than 0, we trigger a timer with a preset time equal to the period. When the timer is up, we update the sine wave by subtracting 10 milliseconds from its period. Let's test it. Add a new scope YT project. Go to the target browser and add the excitation and the system response and start recording. Export the data into a CSV file. Clean it up and download the data to your PC. Import the data into Matlab. Convert the data into a ID data object. The output first, then the input, then the sampling time. Pay attention in the order of these arguments. Open the System Identification Toolbox and import your ID data object. Check your time plot, make sure all looks good. Select the type of model and set the model parameters. Estimate the model and check its performance against the training data. In a real experiment, you will also want to do it against validation data. Keep that in mind. Check the estimated parameters. Now, transfer your model to the workspace and open Simulink. Finally, you can create a closed-loop system and let the PID tuner do the magic for you.